Hello everyone and welcome to our channel Mootechie. It's wonderful to have you here as we dive into a fascinating topic from physical chemistry. Let's get started. Now let's move on to our main subject, Ostwald's dilution law based on the Arrhenius theory. According to the Arrhenius theory of dissociation, an electrolyte dissociates into ions in water solutions. These ions exist in a state of equilibrium with the undissociated molecules. This special state is what we call the ionic equilibrium. Ostwald made a key connection, noting that the law of mass action can be applied to this ionic equilibrium, just as it is applied to other chemical equilibria. This application also helps us understand how the degree of dissociation of an electrolyte changes. Next, we explore the setup for this law. Consider a binary electrolyte AB which dissociates into A to the power of plus and B to the power of the minus ions. The equilibrium state is represented by this simple equation. Now let's look at the concentrations. Initially, at time at equals 0, we have C moles per liter of AB and 0 for both ions. But at equilibrium, the amount of undissociated AB becomes C times 1 minus alpha. Meanwhile, the concentration of A to the power of plus ions becomes C times alpha, and the concentration of B to the power of minus ions is also C times alpha. So let C moles per liter be the total concentration of the electrolyte, and let alpha be its degree of dissociation. These are the concentration terms we work with at equilibrium. Coming up, we'll discuss how this law is tested in a lab. The Ostwald's dilution law can be verified if we know the values of alpha, the degree of dissociation, at different dilution levels. But how do we find alpha? The values of alpha are determined experimentally by using a specific relation. Here, lambda_V is the equivalent conductance at a specific dilution, V, and lambda_infinity is the equivalent conductance at infinite dilution. Their values are found through careful conductance measurements and by applying Kohlrausch's law. Once we determine the values of alpha at various dilutions, we plug them into the equilibrium expression for the dissociation constant. As we continue, let's understand what confirms the law. If the calculated values of the equilibrium constant, K_C, come out to be constant across different dilutions, then Ostwald's law stands verified. A constant K_C is the key signature we look for. Moving forward, we'll see that this law isn't perfect for all electrolytes. Let's talk about the limitations of Ostwald's dilution law. This law holds good only for weak electrolytes, and fails completely in the case of strong electrolytes. The value of alpha is determined by conductivity measurements using the formula lambda_V over lambda_infinity. When you take the alpha values determined at various dilutions and substitute them into the constants formula, you only get a constant value of K for weak electrolytes like acetic acid or ammonium hydroxide. So why does it fail for strong electrolytes? Let's understand this more clearly. Ostwald's law fails for a couple of important reasons. First, the law is based on the idea that only a portion of the electrolyte is dissociated into ions at ordinary dilution, and that it becomes complete only at infinite dilution. However, strong electrolytes are almost completely ionized at all dilutions. Because of this, the method of using equivalent conductance doesn't give an accurate value of alpha for them. Secondly, when the concentration of the ions is very high, the presence of charges on the ions appreciably affects the equilibrium. The ions interact with each other electrostatically. Hence, the law of mass action in its simple form cannot be strictly applied in the case of strong electrolytes. The real-world behavior is more complex than the idealized model. And with that, we've reached the end of our lesson for today. Thank you. See you in the next class.